Hello everyone. Let's continue our discussion on noise protection techniques. So in the last video we saw a technique of shielding, that is basically creating a wall between the aggressor and the victim, and that was very much helpful in protecting the noise between the aggressor and the victim. There is one more technique, there are two more techniques actually. So let's look into the next one. So the next technique that we will be discussing is spacing. So spacing is very simple. It says that you space the aggressor and the victims apart, and you will see less of crosstalk. It's as simple as that. So let's see how do we do this. Aggressor net. You have this aggressor net. You have the victim net, and you just space them apart. It's basically you're increasing a distance between two different basically it's basically two wires between which you're increasing the distance, and as a result of that the two wires are won't couple with each other much. Is that so what we are doing is we are just increasing the spacing between the aggressor and the victim, and because of this, when you increase the distance between aggressor and the victim, your mutual coupling capacitance or the coupling between aggressor and the victim reduces, and if they don't couple, there will be less impact of any of the switching activity on the aggressor on the victim. Okay, so technically if you speak, the reason that mutual coupling capacitance reduces, it lies in the inherent this equation. So mutual coupling capacitance is, or any coupling capacitance, or any capacitance in that case, is inversely proportional to the distance between the parallel plates. In this case, the parallel plates will be the aggressor and the victim. The mutual coupling capacitance between the aggressor and the victim is inversely proportional to the distance between them. And as a result of that, if you increase your distance, you reduce your mutual coupling capacitance, and once you reduce your mutual coupling capacitance, there will be very less coupling happening between the aggressor and the victim, and you save this particular net from getting affected by any of the switching activity happening on aggressor. But now there is an impact of this on the there is some impact of this particular thing, and the impact is there is an increase in the routing resources. So let's imagine we moved this particular net by two steps. Initially the net was present over here, then the net was present over here, now the net is present over here. So before that, if this had been our area, there would have been 1, 2, 3, 4 routing resources that would have been getting accommodated in this area. But now, because of this forceful constraint that we have, that the spacing between aggressor and the victim should be some x distance, and this is forceful, we are not allowed to place any routes in this area. So the same area which was able to accommodate 4 routes, now it is able to accommodate only 2 routes, which is aggressor and the victim. That's all. You can't put any extra routes in this area. And that's a direct impact on the routing resources, because you have to find a different area on the chip to route to route this particular layers, which it had been possible if there was no crosstalk affecting over here. So now the same area which was able to route four nets, now it can route only 2 nets, and the remaining 2 nets which would have been present over here, they have to find out a different way. And on a chip, you're seeing this is only one of the area where you see the impact of routing resources. Imagine if this area was repeated multiple times, or basically if we had crosstalk affected areas on the chip, like let's say 100 or thousands of times, the impact on the routing resources, it would have been huge. It is huge. So as a result of that, you see that there is an increase there is a constant increase in the number of metal layers in the advanced nodes and technologies. We'll talk about that in some other videos, but this is basically the primary reason that you see an increase in the number of metal layers, because on the same level, on the same metal layer, there are not enough routing resources available, and crosstalk is one of the primary reasons for that. Okay, so this is the impact of having having spacing between the aggressors and the victims. But again, it has an impact on routing resources, but it's a very good way to very good way to avoid noise on the victim. And hence this particular techniques are applied only on the critical nets. For example, again the clock, because the clocks are the one that are continuously switching. Let's take an example. Let's look into an example of how does the spacing increases. How does the increase in the spacing affects your glitch. So for example, this was a scenario before. Let's say you have the aggressor and the victim, and you have this aggressor which is switching from logic high to logic low, and you initially the amount of glitch value that would have been seen with this amount of spacing is this value. Now let's try to increase the spacing between the aggressor and the victim, and you will be seeing an impact on the glitch height. So this is how it goes. You increase the spacing between aggressor and the victim, and your glitch height actually reduces. You increase the spacing even more, and your glitch height reduces even more. So this is a very basic circuit that will help us to explain how does increasing the spacing between aggressor and the victim actually helps the glitch height. So glitch and crosstalk delta delay, everything are related to the spacing between the aggressor and the victim. So this is how it actually reduces it. Okay, so next there is one more technique that we'll be looking to protect noise, and that is the drive strength of the victim. So this has been already been covered as a part of some other videos which was called as factors affecting glitch height. So there we have covered the this particular topic. So let's try to revise it again. Okay, and that the topics that we have covered over there, those were actually some of the glitch protection techniques. Let's try to revise, let's try to cover it over here again with some examples. Okay, so again we have the aggressor and the victim, and let's say initially you had something like this. The delay of this particular cell was very huge, and the impact of this particular aggressor on the victim was so high that you see an impact something like this. The slew is as bad as this, as it's shown over here. This is a crosstalk slew. Again, this is a derived slew. It would have been a bump which is present over here, but we have modeled that bump as a part of the slew, and this is what you see over here. So it's a bad slew. So now what we'll do is we'll try to increase the drive strength of this particular victim driver and see what happens. So when you see if this particular things have become more strong, so when this particular inverter becomes more strong, it means that the resistance of the PMOS transistor which is present over here, that has lowered down, or in other words, the size of the PMOS transistor has increased. Sorry, resistance is inversely proportional to area. As you increase your area, your resistance reduces, and if your resistance reduces, this is you see an improvement in the slew. So previously if it was like this, now it will be like this. Even more, if you try to make this even stronger, you see a very good impact on the slew. You see the slew even improves even more. If you make it even stronger, the slew improves even more. So in this case, what we have seen is if you increase the drive strength of your victim, you are actually able to reduce the crosstalk, and the delay also gets reduced. So that impact is already there. On the top of that, you will have an impact on the slew directly. So let's try to look into this in this fashion. So for example, initially you had this amount of slew, and this is again because of the aggressor switching in this area, and that is impacting the victim in this area. And also there is an assumption that the aggressor and the victim are switching in the same direction. So we have taken a look into two cases where aggressor and victim are switching in the same direction, and the aggressors and victim are switching in opposite directions, where each one has got its own problem. So aggressor and victim will be in this case, the aggressor and victim will be switching in opposite direction. Okay, that's the assumption that is present over here. So if you see, because of the aggressor and the victim switching in opposite direction, you see an direct impact on the slew, which is very bad. You increase the drive strength of the victim, and you see how the slew gets improved. Okay, so there is an improvement in the slew as you increase the drive strength of the victim. So let's try to take this particular scenario and put it in some examples that we have taken in the past. So we have done some timing analysis based on some circuits that we have taken. So what we'll do is, in the since I'm running a bit late out of my time, so we'll take this example, we'll take this particular victim drive strength, we'll model the victim drive strength, will model the victim drive strength of this particular circuit and see how does it directly impacts the delta delay, or how it impacts the delay of this particular cell, and how does impact on this delay of this particular cell impacts the data arrival time, and hence the complete equation, basically how it saves us from crosstalk. So let's try to look into all this in the next video. Thank you.